Rickard Söderberg, Chalmers. And Rickard is a professor in the field of product and production development. And very welcome. And the headline for today's speak is Enabling Circular Geometry Assurance. And Rickard, is it okay if someone interrupt during your presentation, or should we take the questions afterwards? Because now
Yeah, well, I think we can take them afterwards.
Okay, good.
So we don't take the time for lunch or...
Yeah, I don't know if this works too.
Is it working?
We can see if we can get that into work. But okay, welcome, Rickard.
Yeah.
And please.
Okay, so my name is Rickard Söderberg. I'm professor at Chalmers. I'm head of the Department of Industrial Material Science. I'm also the director of Winquist Laboratory, which is a center for virtual product realization. And I've been doing research in geometry assurance since the 90s. So I'm research group leader for the research group Geometry Assurance and Robust Design. And this talk will be, of course, about geometry assurance. And specifically, well, I call the talk Enabling Circular Geometry Assurance, because I think a lot of things we do are enabling a new way of working in the future. But it really comes back to a project we are running right now, Digital Quality Assurance for Sustainable Industry. It's we're in the middle or slightly more in the project. It's a Vinnova project. It's quite high TRL level. It's in the program Uppskalning för hållbar industri. We have Fraunhofer Chalmers Center, we have Volvo Cars, LK, Polyworks, IPS, RD&T Technology, Saab, and Chalmers in the project. And as in this session, what we are dealing with is, of course, geometrical variation. We have variation in all the industrial processes. Even if the machines and the processes are getting better and better, the requirements are getting tougher and tougher, so the problem still remains. So when we manufacture parts, we get variation in the form and the size of the parts. When we assemble them, we add variation. When we join them, we add variation from the joining process also. And together we could get problems. First, during assembly, the parts don't fit. We need to scrap or rework or do something that costs money. Or it could be a problem with the function. If the product is shipped to the customer and it needs to be taken back, it costs a lot of money, a lot of bad will around that. And it could be like what we see. So typically the split lines, the gap and flush between all the exterior panels of a car. We want them to be parallel, small, the same, and look nice, because that gives a good quality impression. So it all comes down to the effect of variation, basically. And when we talk about geometry assurance, we mean the set of activities that aims to minimize the effect of geometrical variation in the final product. So typically we do things in early concept or design phase. We have a specification of the product. We need to break that specification down into requirements on sub-assemblies and finally on parts. For us in this room, we need to specify tolerances, locators, datums. Typically, we can do that with help of some simulation tool to iteratively see what tolerances, if I put these tolerances on the part, will I fulfill the requirements on the product? In pre-production, we do inspection preparation, we do offline programming of all the inspection devices, and then during production, we inspect. We use inspection data to fix ongoing problems, learn about the processes, but also give feedback to design. So we know when we design the next product, what variation to expect from a supplier, a machine, or a process. So most companies are involved in this loop in one way or another, more or less sophisticated. In this particular project, we have run many projects since the 90s. In this particular project, we address some problems. The first is there is no uniform digital standardized way to specify and verify geometrical requirements. There are standards, but they are not in use fully, and there are a lot of difference in how they are used. There are no efficient way to measure and evaluate details independent of the fixture. No efficient way to automatically configure an inspection task. No efficient way to return and verify measurement data against requirement. So all this makes it difficult for companies in the chain to work together, OEMs, SMEs, difficult for large and small companies to participate. If we see a future more digital marketplace, when you get a job from this marketplace, you put the result back and so on. It's difficult to collaborate. So, and we also think that in the future, if we want to have a circular system, we need to know a lot about the parts. We need to know the requirements. We need to know how it's circulated, all these things. So what we do in this project, we address those questions. So specify, fixture, measure, and analyze. So basically there are 4 work packages. And in the first one, we address how to specify geometrical requirements digitally. When it comes to fixturing, how can we verify geometrical requirements fixture independent? Measure, how to configure and optimize an inspection cell automatically. And when it comes to analyze, how to evaluate the part or subassembly virtually. So I will go through these questions one by one and tell you what we have done in the project so far. So start with specification, how to specify geometrical requirements digitally. And what we are talking about here is we have like an information loop. As I said earlier, in the geometry assurance process, in early design phases, we need to break requirements down. We need to specify tolerances, locators, datums on parts. Typically, we have an environment where we do some things in the CAD system. Many companies are using a CAT system, computer-aided tolerancing system, where we do the variation simulation to assist tolerance analysis and to come up with tolerances to put on the parts to fulfill the requirements of the product. So there is information going between the CAD system and the CAT system. When we do the inspection preparation, we need to know what are the requirements. When we evaluate, when we have done the inspection and we have a database with a lot of inspection data, we want to do an analysis, we want to know the requirements. So we have some type of computer-aided inspection system. So, and information needs to flow between those systems. And they do today, but very company specific and with a lot of different solutions. So in this project, what we aimed to look at was how can we go from, if we define the requirements in the CAD system, the GD&T in the CAD system, how can we import it into the CAT system? In our case, it's RD&T that we develop, and do the simulation based on that. Or how can we take inspection data and import it into the CAT system to do variation simulation based on inspection data? Because that can be quite interesting. So we're looking at the new AP, the STEP AP 242 and the KIF standard. And they seem to have a lot of similarities, of course. The idea is to basically import the information, the GD&T, directly into the CAT system. We have looked at both, but I will talk about KIF now in this presentation. So KIF is continuation, extension of the DEMI standard for inspection. It has a lot of libraries, it's a big thing. We have only looked at the number one, the MBD part of it, so how we can specify the requirements, the PMI part. And it looks quite okay so far, we can say. So what we have done, we have in our CAT system, in RD&T, we have built a GD&T library, so we're actually able to define features, holes, slots, planes, and on those features we can define tolerances, GD&T. So that is inside RD&T. But what we have tested now is to export from the CAD system. If we define all those GD&T in the CAD system, we can export it in a KIF format, and we can import it into RD&T. So what we see here is what is imported into RD&T, into the tolerancing system. And it's not only just dead information or pixels, it's actually semantic information. So if we see we have locating scheme, ABC, we have some position tolerances, flatness, and everything, all this can now be read by the system. So actually, if I want to do a simple tolerance analysis, I just want to vary the locating scheme, the ABC. if I have variation in the ABC, what will happen? So just to demonstrate that. So what I do, I go in, I select my locating scheme ABC, and then I can run a variation simulation. I can show the result in color coding like that. It's quite good thing to just check the locating scheme. Is it stable or not? Where do I get sensitive areas? So this is a good first check. I can change the numbers and it will change on the screen. We haven't done it yet, but we can also write KIF, so we can write it back to the CAD system. Here is another example, a small engine, a small assembly with some tolerances relating to each other. We have imported it via KIF, and we are running a variation simulation, so that critical dimension between some features here, and you can run the simulation. So seems quite well, works well so far. We compare to STEP, we see it's a little different how features are defined, so we will come back to that. So the next question is then, how can we verify geometrical requirements fixture independent? So today, most companies, if we want to measure a part, inspect a part, like the one on the top, we need to design a fixture. Someone needs to manufacture it. It needs to be transported. You need to prepare things. You need to rig. You need to measure. You need to store the fixture. You need to do a lot of things. So, and there are lead times for this. So actually, large OEMs, they have lots of these fixtures, and they cost a lot, and they take a lot of time to design and manufacture and get them. Another thing, often when you put the part in a fixture like this, you often over-constrain it. So you have a number of clamps. So you bend the part to fit the fixture. That could be good for some reason if the fixture reflects the final position of the part in the car in this case. That's good, but you don't get the real shape of the part. You get the shape in the fixture position. So if we want to use inspection data to do variation simulation to put parts together, this is already dead. I don't get the effect of bending and spring back if I take inspection data from a dead part. So what we suggest with what we work with here is that we take away the need for those specific fixtures. We have another way. We rig the part on 3 spheres. We scan the part, and then we do a calculation of the real shape in our system, in RDNT in this case. We do a gravity compensation, so we get the real shape in free form of the part. And then you could either evaluate it as it is in free shape, or actually we could have a virtual fixture. A virtual fixture is just some extra points where we clamp the part. So we can bend it. This is a real, but we can have a virtual fixture, just some points, and we can actually bend it in the system if we want to evaluate it like that, but do it virtually. So it gives us both the real shape and possibility to evaluate in 2 different ways. So that, of course, we can do more analysis, we can understand better, we can do all the analysis, evaluation that we've done before, and it takes away the need for all the fixtures. Could be a good thing. We are also now elaborating with, could we assist? You saw in the picture there was a girl scanning. We could do this, of course, with a robot, and then we can ask ourselves, where should we put the robot to have the best reachability? Or should we have some robot helping a human? So we are elaborating with these things also to basically do path planning for robots or for humans or a mix. Okay, talking about measuring and inspection then. The next question we address is how to configure and optimize an inspection cell automatically. And if the earlier examples were from the automotive industry, this is from Saab Aeronautics. We have a physical inspection cell with a rotation table. We have a part that we are supposed to inspect. We have a laser radar that can go up and down. And we want to, with this system, we want to automatically create a code for this cell to inspect a number of features, holes and slots and whatever. And we can do that automatically. So the first thing we need to do, here we use IPS software to do all this. So the first thing we need to do is we need to take in the geometries into IPS. So the fixture, the product that we want to inspect, the features we want to inspect. We have some tooling spheres for alignment to know where we are. So we import that, and then the inspection preparation starts. First step is to look at all the features and see what is the best way of inspecting this feature, because you have some parameters, some variation how you can inspect the feature. So we find ways of inspecting each feature. That's the first thing. So go through all the features. And then we have basically the traveling salesman problem. We have a number of features, so how to go between the features in the fastest way. So that is then optimized. So we have a linear and a rotation degrees of freedom to play with, and we want to take the features in a most efficient way. So we can calculate that. So this shows in the virtual world, and then we run the same code in the real world. Yeah. So basically what this says is that first we do it virtually and then we do it in the real world, and it works. Okay. The last question we are asking ourselves here, how to evaluate the part or subassembly virtually. So normally when we do tolerance analysis using variation simulation, we have a model. So in the middle here, I have a model. If it's a non-rigid model, I have the geometries are finite element meshes. So I have some meshes. I have defined how they are connected to each other. Spot welds. I have locators, fixtures, contact points, and so on. And then we can feed this with variation. So if I have inspection data or if I have requirements, as we said from the first question, it could be GD&T digitally. So I have requirements or I have inspection data representing the variation of the parts. And then we can run a variation simulation. We use Monte Carlo simulation then. And then I get the result. So the result could be a statistical distribution in some critical dimension I want to analyze, or it could be a color coding showing the whole variation. Depends on what we like or what we need. So this is how we normally do things. And we say, okay, if it's red, or if it's, I don't have any limits here, but if I have some tolerance limits and we are outside the tolerance limits, then it's not good. We need to do something. So this is how we work and how most companies work. The question we are addressing here is that, let's say I have a sub-assembly here. I have done a variation simulation. I see, okay, it's red in some areas, it's green in some areas. Is this okay or not? I could, of course, put some measures, also critical dimension. I have a position tolerance here or surface profile tolerance or something. But what if this sub-assembly is assembled to another sub-assembly that is stiffer? What would happen? This would probably form after that. So then the question is, how severe is this variation? If it's very slender, if it's a rubber mat, probably doesn't matter at all. So what we have then come up with as an idea, as a complement to variation simulation, is to look what is the energy needed to put that subassembly on another subassembly in the next assembly step. We're using something called strain energy density, but the idea is basically say that the subassembly is quite stiff, and I position it to something that is equally stiff, or if it's quite flexible and I position it to something that is stiffer. So what we do is that for this simulation, we just assume that in one case, the subassembly was sheet metal, and then we assume it to be plastic, same, just change the material parameters. So then we can see that if it was sheet metal and I would position it to the gray part, it would require the 786 Newton millimeters. If it would be plastic, it only would require 7 Newton millimeters energy. So this gives a hint of the severity of the variation. So I have same variation, but depending on where it goes and how much energy is required to put it in the next assembly step. That could be an extra information to help us to understand, is this a problem or not? Sometimes you see companies evaluate flexible parts as if they are rigid. And then that means you will scrap parts because they're outside tolerance, but if they bend and they form, doesn't matter. So this is an extra thing that we can use. So the variation is one thing and the energy needed is another thing. Okay, so this we have gone through. How can we specify requirement digitally? How can we verify fixture independent? How can we configure, optimize an inspection cell automatically? And how can we evaluate the part for subassembly virtually? So a complement. And this is, as I said, in this Vinnova program is quite high tier level, and there are we have expectations of transferring the results. So this is now actually, a lot of these things are actually being rolled out to all the Volvo car factories in the world. Same for Saab. We have sales offices for Polyworks and users of RDNT and IPS over the world. So we think that we can get a fairly good spread of these results out. And in general, if we look at sustainability, we think that we can contribute to a climate neutral circular production through increased degree of digitalization and automation. With all the things we described, we reduce transport of physical details, travel, physical test series, we get rid of that. And when it comes to variation, of course, we reduce variation, we reduce lead time, we reduce programming time, we reduce need for physical documents and physical fixtures. So a lot of things that I think we need to do to prepare for a circular system. If we want to take parts back, run them again, we need to know the requirements, we need to know the history behind them. So I think an increased level of digitalization is needed for that. So that was what I had to tell you about this project. Thank you very much.
Any questions?
Yep. I can talk. Very interesting. Things are happening actually. Looks good. Your scanning of that part with the laser scanning and so on, how dependent are you on that being a robust scanner versus could you go into a cab, for instance, or a body white and scan from the inside, like that?
I think normally the scanner has like a tolerance, you need to be positioned in a certain way and so on. So I think if you follow the requirements of the scanner, I think you're safe. What we showed also with the automatic path planning for a robot or a mannequin, I think we could actually do the optimization also. So we are securing that we get the best out of the scanner.
Yeah. You might have
but that's a good that's a good criteria for the path planning. To have that.
But you could also have fixed points so that you know where the scanner is.
Yeah. Could be. As it is right now, we know that if we are in this area, the scanner will give a good result according to its specification.
Yeah.
Yeah.
But when you simulated the result without fixture, you maybe mentioned it, but the material properties like E-module and so on, you must calculate with those.
Yeah. So everything I told about now is non-rigid variation simulation. So it's based on a geometry, which is a finite element mesh, and we have the material properties. Yeah. So because then we need all this bending and everything, spring back and everything. So this is non-rigid. Yeah. I think you need to look at that.
Yeah.
A lot of companies today are doing tolerance analysis, variation simulation with the assumption that the parts are rigid. And there are some tricks where you can bend the parts actually, and you can come pretty close, but we have been working with non-rigid simulation for 20 years. And it's now, of course, in the beginning, 20 years ago, it was a problem where to get the meshes from. But most companies solve that today. They have a department that can give them a mesh. So, and then it takes a little more time, so on, but it gives such much more understanding, and it's not for the user, instead of 6 locators, you can have some more clamps. Yes?
I have a little bit different question. I think the nice thing with this method is very generic. So I think it can be transferred to many different components.
Yeah.
But at some point there will be a limit. At least when you have a gear on the component, then this will create some problems because the gears are measured in a different way. And I would say this method is already implemented for this component. I know this discussion internally when we talk about MBD, it becomes difficult. So how far do you think this can be generalized? And is there any discussion about including gear technology in this kind of...
And gear, you mean gearboxes or...
just the component gear with the teeth around it.
Yeah. As you saw from, of course, to be honest, we worked a lot with body components and this, but one reason why we are implementing the GD&T library and the standards is to be able to work more with machine parts. And then, of course, gears with the events and everything are quite specific, but you probably need to do a module like some features to handle the gears. But I think it could be treated as anything else, but with little specific extra things.
I think so too, but it's
I
was wondering if there was...
No. I mean, the gear and the contact between the gear is quite a specific problem, of course, and the contact will vary based on the tolerances of the gears and so on. But if you put up that model, you should be able to analyze whether if the contact point is moving around. So, and as I said, that's one of the reasons we are implementing GD&T. Normally we do variation simulation. We put some tolerances on, we vary in the surface normal. And then when we understand how it works, we put the GD&T on the drawing. In this case, we can of course import the GD&T and see if it's working. So you can go both ways. Okay.
Yeah.
Thank you very much.
I would like to